We're going to talk about today about how do we resolve stress on a particular plane of interest. Now, let's imagine that we are working with a sample. So I'm looking at a sample, my coordinate system, original coordinate system y. I'm going to do 2, 1. So I have a sample like this, and I have some stress data. So I'm pulling it, I'm shearing it like this. So I have some stress state that's equal to sigma 1, sigma 2, 2, and then there's again the normal. So it's going to be some stress in the 2 direction. Again, my normal 2, 1, so 1, 2, sigma 1, 2, and everything else is 0, 0, 0, 0, 0. Plane stress. So what would happen if I wanted to know, or if I wanted to rotate, what if I wanted to look at it from some new coordinate system? Or if I wanted to look at it, let's say I wanted to look at the stress along this orientation. So let's say I had a new coordinate system where now this would be my 1 prime direction, this would be my 2 prime direction, rotated some arbitrary angle theta. So how would I figure out what's the stress state of that, again, same sample, same stress, same original stress state, but how would I figure out what is the stress rate in this new coordinate system? And again, this is important for metals, for example. When you have a uniaxial tensile test, metals will typically fail at basically these angles. You'll see the shear banding at these 45 degree angles from where the normal stress is applied. Why does that occur? Or from our example from rolling titanium. So if I have titanium sheet, I know that my Young's modulus is basically stiffer along that kind of, remember that C, excuse me. So we have hexagonal close packed. So the Young's modulus along the C direction is stiffer than along these kind of other A, B directions. So I want to know, or I want to kind of see, or figure out, I want to be able to tell what is the stress state at some arbitrary rotation, or if I kind of again rotate my coordinate system, what are the stresses in this new coordinate system? So I'm going to figure out what's my new coordinate, sigma 1, 1 prime, sigma 2 prime, sigma 1 prime, 2 prime, sigma 2 prime, 2 prime, etc., etc., etc. I want to know what are those values, and are the rest of these 0 too. So that's what we're going to kind of get into today. So one way that you could solve this problem is by looking at it from a statics perspective. So you have an inertial coordinate system, you have a kind of new coordinate system that's offset by this angle theta, so just like you see kind of here, and you can kind of just rotate and resolve the stresses in the new coordinate system. So you can do a lot of statics. You can sum all the forces in the x direction in the new coordinate system, or all the forces here. I know this is trivial for you all to do. And then eventually, after lots of rearranging and trig transformations, you can get this expression. And then you can solve, again, generally for any value of theta, you could plug in and figure out what are the stresses in this new coordinate system. Now, if you can do this, congratulations, your statics professor was amazing. But this is a hard thing to do every single time that you want to kind of solve problems. So instead, we can do this a little bit easier using this transformation matrix T and a little bit of linear algebra. So if you instead basically write or kind of use this transformation, again, this is just a coordinate system transformation matrix T, where C is cosine of theta, S is sine of theta. And now, if I want to rotate or create or look at what are my stresses in my new coordinate system, x prime, y prime, xy prime, etc., all I have to do is do my transformation matrix dot with the original stress tensor right there. And I can figure out what are the stresses in this new coordinate system. That's it. That's all you do. And you can figure out all this answer. And you can do the same thing for strain as well, except again, from our infinitesimal strain theory, this is where kind of some annoying things come into play. So you could do the same exact thing for strain, but you have this extra step where, again, you're converting from the, again, this tensor definition of strain. So we know here our tensorial definition lost my pen's down for the count here for a second. Let's see if I can get it back. Here we go. We know from our tensorial definition of strain that this 1, 2 is equal to half of gamma 1, 2. So here you can see that to get to my new coordinate system, I'm going to take my original coordinate system here, where I'm given this value, and I'm going to convert it here into tensorial definition. So I need to multiply this value by a half. Then I'm going to transform it, and then I'm going to transform it, rotate it here, and then I need to multiply this again by 2 to get back to my basically shear definition of strain. So that's kind of the key idea of working backwards from here. So my original value, multiply it by this R, or the transpose here, that inverse on my Rother's matrix to again convert it to tensorial, because I need to convert to this tensorial definition in order to do this rotation. That's kind of the key operator. This transformation matrix must only be operated on your tensorial definition of stress and strain. And then afterwards, I can multiply this again in order to get back into my engineering shear strain definition. So that's kind of the key idea here, using this basically this linear algebra approach to resolving and rotating coordinate systems. So that would be the key approach that I would use. However, you can use one of the more common, or actually not one of the more common, but another approach, which was developed by a very famous engineer called Moore. And hopefully you've heard this before, from Moore's circle. So we'll get to the back a little bit into that into kind of this next video. But the kind of key idea is, before we get into that, typically we find when you transform to a new coordinate system, you want to figure out where materials are going to fail. So basically ceramics, brittle oxides, glassy polymers, they're all going to fail at maximum normal stresses. And metals or composites are going to typically fail at maximum shear stresses. So in order to find the maximum stress state or the principal stress state, we're going to differentiate with respect to 2 theta, and we're going to find, actually these come from kind of our previous definitions up here. Where are we at? So if you figure out, if I want to maximize if I want to find my principal normal stress state, I want to figure out where my sigma, 1, or actually I want to figure out where my normal stresses are maximized, i.e. where sigma xx and sigma yy, where are they maximized? So I'm going to take the derivative with respect to theta and set it equal to 0. So my maximum normal stress is going to be this sigma 1 value. So sigma 1, my kind of second, or my minimum, or not my minimum, but in that plane, the next largest shear stress, or usually my minimum normal shear stress, is going to be the sigma 2. So the principal maximum normal stresses, and sigma 1 is going to be greater than sigma 2. And you can do the same thing for shear. And this is going to become much more clear when we actually do this kind of Moore's circle construction. So from some simple geometry and some circular symmetry, if you have a stress tensor that looks like this, right now, 10, 22, 10, 6, 6, you can use kind of this idea and this relationship from circular symmetry. Hopefully you remember this looks very similar to a circle. You can use this idea of Moore's circle and figure out and plot in stress state. So here we're going to look at tau, the function of, so our shear stresses and our normal stresses. So we could see here, our stress tensor is going to basically look like a coordinate system. So here, I know that I have a coordinate here. So if we're looking at just this right here, 6, 6. So I basically have, okay, what's my coordinates here? Well, I have a normal stress at 22, and I'm going to have a shear stress at 6. I'm also going to have a normal stress at 10, normal stress, sigma, sigma, tau, tau. I also have stress here. But due to circular symmetry, I now also have a point at -6. So here, here. So my circle is going to kind of intersect here. So my maximum, my normal stress state right now, I have a point here that's going to intersect here, and a point here that's going to intersect here. I'm going to erase that last point, but this is my stress state. If I want to find my maximum or my principal normal stress state, I need to rotate from here clockwise some angle theta. So I need to, if I want to be in my principal normal stress, I want to maximize my normal stresses. My normal stresses are maximized here, which is going to be sigma 1, and then my minimum is going to be sigma 2 right here. So when I'm lying flat here, I am in a basically stress tensor like this. Sigma 1, sigma 2, everything else is 0. That's it. That's kind of what you're dealing with, or at least in the 2D sense. We'll show that the 3D sense it gets a little bit more complicated. But really, I'm in a stress state just like this. So how do I figure out what is sigma 1 and sigma 2? Well, let's see. I've got a point right here, so 22. There's some center value right here. But I know that this point is at 6. So I know that I have a length right here, 6. I have a point at the center here, and theta. I know that there's going to be some radius here that I could calculate from just the length of this line. And then from that, you can do some simple geometry and figure out the rest of these values. So we'll do that example in the next video and then figure out how to get into your principal normal stress state and use Mohr circle to solve problems in conjunction with basically the linear algebra approach. So I'll see you all.